So this is section 13.1. We are talking about the premises of geometry. Okay? A premise is like a given statement. And then from that premise, from that thing that's given, we can build upon it and find out something else that is true. Okay, so here we go. We are embarking on a journey of proving geometry to be true. Not through inductive reasoning, but through deductive reasoning. Much like these great mathematicians did. Thales, Pythagoras, Plato, Euclid. Some of these names might sound familiar, like Pythagoras and the Pythagorean theorem. Euclid, it's called Euclidean geometry because of him. Okay? These mathematicians created sort of a, I'll call it a society, where they would get together and they would prove certain things to be true. Well, we are going to attempt to do much the same thing. We won't prove everything, not like them, but we will prove a lot of things. Here are a couple new vocabulary terms. A deductive system is a set of premises and logical rules used to organize properties of geometry in which theorems are proven and terms defined using knowledge stated previously in the system. Now this deductive system, that's a very wordy explanation, okay? But here's the point, and this is what we're going to do. We're going to use things like definitions, things like postulates, and we are going to build upon our knowledge of those things by using them to prove other things are true. And that's exactly what a deductive system is. We know that deductive reasoning is where you use facts. Well, we're going to use facts to prove other new facts, right? And this thing's just going to keep rolling over because once we prove a new fact, we're going to use it to prove another new fact, and so on and so on. Okay? And we're going to create what we call a deductive system. Now, a theorem is a conjecture that can be proven using deductive reasoning. Think back to inductive reasoning, when we based our conjectures off of patterns or observations. If that pattern broke down, then our conjecture was wrong. Well, now when we use deductive reasoning and we prove something to be true, it becomes a theorem. And there's no going back on theorems. They become facts. They cannot be wrong. A postulate is a statement that is accepted as true without proof. And I'm going to show you a nice long list of postulates. They are so simple that you're going to say to yourself, well, yeah, of course that's true. And this is exactly what happened when people like Pythagoras or Euclid or Thales or Plato got together with their friends. They all sat around a table, not really, but maybe, and they said, well, what about this? And they all came to an agreement that, yes, that's so simple. We're not going to prove that. We're going to just accept that as true. And you'll see what I'm talking about here in a second. Okay, so we have talked a lot about inductive and deductive reasoning, right? Inductive, we drew conclusions, conjectures based on patterns and observations. Deductive is all based on fact. We are definitely dealing with deductive reasoning now. So these are the four types of premises. Definitions. We have defined a lot of vocabulary terms. Geometry is very much its own language. We will use those definitions to help prove other things to be true. Properties of arithmetic, equality, and congruence. These are the rules of algebra, and I'm going to show you them in a second. Postulates of geometry. Just got done talking about those. Those are the things that are so simple, we just accept them as true without having to prove them. And finally, proven geometry conjectures, or theorems. Once we prove something to be true, we can then use it to prove other things to be true. Okay? So here we go. The properties of arithmetic. You already know these because you're good at algebra, but you probably don't know the names of them. You are going to have to know the names of them because when you write a proof, you are going to have to Write down the name of the property that you are using. The commutative property of addition says A plus B equals B plus A. You already know that because 3 plus 2 equals 5 and 2 plus 3 equals 5. It doesn't matter what order you add in, right? The commutative property of multiplication. A times B equals B times A. The associative property of addition. A plus B plus C equals A plus B plus C. Whew, okay? All this is saying is when you have three things, it doesn't matter which two you add together first. You're going to get the same thing. The associative property of multiplication. The distributive property. We all know the distributive property. The reflexive property. A equals A. Well, of course it does. 3 equals 3. Anything is equal to itself. The transitive property. If A equals B and B equals C, then A equals C. This property often takes the form of the substitution property, which says that if B equals C, you can substitute C for B. Right? This becomes an issue because in some cases, and you'll see as we go, the transitive property is the property that is being used. In other cases, you could use the transitive property or the substitution property. Okay? Sometimes they are interchangeable. Sometimes they are not. The symmetric property, if A equals B, then B equals A. That makes sense? The addition property, we've talked about this one recently. If A equals B, then A plus C equals B plus C. In other words, if you take the same thing and add it to both sides of an equation, you haven't changed anything. They are still equal. Subtraction property, same thing except subtracting, right? Properties of equality. The multiplication property. If A equals B, then A times C equals B times C. The division property. The square root property. The zero product property. This is a good one. If A times B equals 0, then either A equals 0 or B equals 0, or they both equal 0. Right? That's very logical. You already know that to be true. Now you have to know that it's called the zero product property. Definition of congruence. Right? If AB equals CD, this is talking about the measurement, the distance from A to B, and the distance from C to D, because there's an equal sign, right? If AB equals CD, then segment AB is congruent to segment CD. And conversely, if segment AB is congruent to segment CD, then AB equals CD. If the measure of angle A equals the measure of angle B, then angle A is congruent to angle B. And conversely, if angle A is congruent to angle B, then the measure of angle A is equal to the measure of angle B. You're sitting there saying, of course, I know this. Well, the reason that we are defining congruence now is because when you transition in a proof from equality, things being equal, to congruency, things being congruent, you need to state that you are using the definition of congruence. We have to justify everything in a proof. Now it says down here, congruence is defined by equality. So you can extend the properties of equality to a reflexive property of congruence, a transitive property of congruence, and a symmetric property of congruence. This is left for you to do in the exercises. So this is something that we'll be doing as we go. Now we get into the geometry postulates. These are those things that are so simple we don't have to prove them to be true. The third set of premises is specific to geometry. These premises are traditionally called postulates. Postulates should be very basic. They should be useful and easy for everyone to agree on with little debate. For example, the line postulate. You can construct exactly one line through any 2 points. In other words, 2 points determines a line. Well, I think we'd all agree that that's true, right? We don't need to prove it. The line intersection postulate. The intersection of two distinct lines is exactly 1 point. Segment duplication postulate. You can construct a segment congruent to another segment. Angle duplication postulate. You can construct an angle congruent to another angle. These are things that you're sitting there like, no kidding, right? Now we have to know the names of these postulates because we have to name them when we use them in a proof. The midpoint postulate. You can construct exactly one midpoint on any line segment. Angle bisector postulate. You can construct exactly one angle bisector in any angle. The parallel postulate. Through a point not on a given line, you can construct exactly one line parallel to the given line. And the perpendicular postulate. Through a point not on a given line, you can construct exactly one line perpendicular to the given line. Segment addition postulate. If point B is on segment AC and between points A and C, then AB plus BC equals AC. We have an angle addition postulate. Linear pair postulate. We've talked about linear pairs. Corresponding angles postulate. If two parallel lines are cut by a transversal, then the corresponding angles are congruent. Conversely, if two coplanar lines are cut by a transversal, forming congruent corresponding angles, then the lines are parallel. We've actually already worked with this in some exercises. These are the tools in your toolbox. Now, the students that do the best or have the most success with proofs are the ones that know what's in the toolbox, they know what they're called, and they know when to use it. The students that struggle the most are the students that they don't understand what's in their toolbox. They don't know what it's called, and they don't know when to use it. You must know these things. If that means you study it night after night after night, then study it. If that means just by using it, because we're going to use these things a lot, you start to learn them, then that is fine as well. Okay? But you need to know what tools are in your toolbox.